Welcome back to the series. Today, Kane will be discussing radiation monitoring and how it is being used in a range of different application areas. So Kane, what will you be talking to us about today?
From reading background radiation to scanning for specific radioactive materials, photonics has been used to aid in an array of different application areas for detecting radioactive materials for decades. As radiation is something we can't detect with any of our 5 senses, it wasn't even until the turn of the 20th century before we were really aware of what was around us. As a result, we have to use the effects of the radiation and its interaction with the environment to measure it.
Why do we measure radiation, and how can we perform these measurements?
Ionizing radiation wasn't really studied until the discovery of X-rays in 1895, and then the further study by Henri Becquerel, Marie and Pierre Curie on similar rays that naturally occurred in certain materials. This discovery of radioactivity heralded a new technological age in many fields such as medicine and power generation, but also led to a better understanding of the dangers of such materials. It is important then to be able to monitor for radioactive materials, be it for environmental reasons to make sure that nuclear power plants are safe and not leaking any harmful substances, or for security reasons when checking vehicles crossing borders, for example. In addition, where there have previously been disasters involving radioactive materials, such as the disasters in Chernobyl in 1986 and the Fukushima Daiichi power plant in 2011, radiation detection is crucial for being able to monitor how these affect the areas surrounding them over the centuries to come. Because we can't see the radiation being measured, we need to use how the radiation interacts with the surrounding environment. The main way of doing this is by using a scintillator over an optical detector. A scintillator is a material that when hit by ionizing radiation exhibits fluorescence or phosphorescence of visible light. This light is then captured by the detector for measurement. The scintillator is chosen based on the type of radiation that you're looking to measure, how energetic it is, the speed it decays, and the wavelength of light you need for your detector. The light collected from the scintillator at the detector can then be used to analyze the sample.
What kind of detectors are used?
Scintillation detection has been around since 1903, but as it only produced faint light visible via microscope, it was imprecise and impractical outside of lab spaces. However, with the development of the photomultiplier tube, or PMT, which uses a series of dynode stages to increase the number of electrons through the device, this allowed even small instances of incident light from the scintillator to be detected by multiplying the current created by as much as 100 million times. The combination of this high gain coupled with low response time made these devices perfect candidates for a variety of applications and gave birth to the modern scintillation detector. Changes in the amplification circuitry surrounding PMTs, such as the move from vacuum tube circuits to transistor-based circuits, improved the performance to what it is today. More recently, arrays of silicon avalanche photodiodes paired with quenching resistors have been fabricated into multi-pixel photon counters, or MPPCs, which are more commonly known as silicon photomultipliers, or SiPMs. As this technology improves, it is proving a popular alternative to the PMT, especially in applications that require portability.
SiPMs or PMTs?
PMTs are still unrivaled for applications that require very low light counts, because inherent noise in the silicon material means that PMTs have a much lower dot count and therefore can detect much smaller numbers of photons. They also provide a much larger wavelength response range, whereas the response range of silicon inherently limits SiPMs. However, for specific applications within that response range with mid to high light counts, such as for radiation detection, SiPMs can offer advantages. Firstly, PMTs require around 1000 volts to operate, which for portable devices can be an issue, whereas SiPMs operate in a range of around 35 to 60 volts depending on device type. Secondly, unlike PMTs, SIPMs are unaffected by exposure to bright light sources such as sunlight, which makes them much more suitable for handheld detectors that may travel through a variety of environments. SIPMs are also less affected by other environmental factors, though both PMTs and SIPMs can be damaged by ionizing radiation over time, as it can create defects in the crystal structure in the case of SIPMs, and the glass, photocathode and diodes of a PMT. With this in mind, PMTs are still the detector of choice for large static detectors that are looking for small radiation signatures, such as those in radiation portal monitor systems for heavy goods vehicles. However, for smaller systems such as handheld and wearable systems, as well as those used on drones and robots, then SIPMs offer a great alternative. In addition to being market leader in PMT technology, Hamamatsu developed new SIPMs that are specifically designed to be used for scintillation detection by reducing cost, operating voltage and the temperature coefficient. Our S14160 series SIPMs are perfectly adapted to these kinds of applications and are tileable to allow them to be arranged to the needs of our customers. Please get in touch with your local Hamamatsu office to find out more.